Hi guys, my seminar topic is noise in amplitude modulator receiver. First of all, I have drawn a block diagram of the AM receiver where a noise gets added with the modulated signal while when it is passed from the transmitter to receiver. Like as we can see here, S of t is the amplitude modulated signal, which where W of t is the wideband noise which gets added to the modulated signal while transmitting it. Then band pass filter is used to reduce the frequency of the incoming noise, and it makes the noise wideband noise to a narrowband noise. Envelope detector, here the envelope detector is used to separate the noise and the modulated signal. Then after the envelope detector, a capacitor is used, which is used to block the DC components from the demodulated signal. Then there we can gain our message without any noise. First of all, to find the noise in an amplitude modulated signal, we need to find a term called figure of merit, where figure of merit is nothing but the ratio between the signal to noise ratio of the output to the signal to noise ratio of the input. The input signal to noise ratio is also called as a channel SNR, which is the signal to noise ratio which is calculated before passing the signal into an envelope detector, and the output SNR is calculated after passing the signal to the envelope detector. Now let us take a message signal. Here we need to find the average power of the message signal. Let us am considering the average power of the message signal as P. Then the formula to find the average power of the message signal is E into mt the whole square. So here the equation is written. Then the average power of the message signal is calculated as AM square by 2, which is a predefined term. Then let us consider the carrier signal, which is nothing but AC cos 2 pi FCT. Then S of t is the amplitude modulated signal, and the equation of the amplitude modulated signal is given as AC 1 plus Ka m of t cos 2 pi FCT. Yeah. Then to find the signal to noise ratio, uh, let me take the average power of the modulated signal, AM modulated signal. Yeah, here it is same as we calculated the average power of the message signal. Here also E into S of t the whole square. Then here I am just taking the square terms inside. And after that we are calculating the average power for individual terms. For one it is as always 1, for Ka it is Ka square, and for message signal as we saw earlier it is P, it is indicated as P. Then for the carrier signal it is AC square by 2, as it is AM square by 2 in message signal. Then the average power of the S of t is written as shown. Then the average power of noise is n naught omega, where omega is the bandwidth of the incoming message signal. Then here we are gonna find the signal to noise ratio of the channel, which is nothing but the input signal to noise ratio. So we need to divide the equations of average power of the S of t and average power of noise to get the signal to noise ratio of the channel. Then let us take this equation as A. Then we need to find the signal to noise ratio of the output. For that, I am considering the equation which is gonna be passed through the envelope detector, which is nothing but x of t is equal to s of t plus n of t. N of t is nothing but the narrowband noise. Then here is the equation for the n of t, the narrowband noise. Then we are gonna substitute these two equations in the first equation, which is nothing but the equation of the AM modulated signal. Then here I've just multiplied the AC terms with 1 plus Ka m of t. Then as we can see from the first two terms, cos 2 pi of ct is common. So let me take those two terms as common. Then after passing this through the envelope detector will allow only the message signal components and it will neglect the carrier components. So to find that, I've just taken the root square to the terms which is not a carrier. Then square is used to compensate it with the square root. Then let me take the first two term as A and second term as B. From the above equation, we can see that A is much greater than B. So square root of a square is equal to a. So then b can be neglected from this term, and we get the equation of y of t. In y of t, the AC is a DC component, AC Ka m of t is a signal component, and n I of t is a noise component. Then this signal is passed through a DC blocking capacitor where the DC component gets neglected. After that, the output of the capacitor is y of t. Where the AC Ka m of t is a demodulated signal and Ni of t is a demodulated noise. Then for the next step to calculate the SNR of the output, we need to find the average power of the demodulated signal and average power of the noise as it was done in SNR channel. So as we know that average power of AC square is AC square and Ka square is the same Ka square. The message signal is P as we found already. Then the average power of this demodulated noise is nothing but the twice of the average power of the input noise, which is nothing but n naught of omega. Then the SNR output is found by dividing the outputs of average power of demodulated signal and average power of the noise. Then, as I already mentioned, figure of merit is nothing but the ratio between the output SNR and channel SNR. So we are dividing the equations A and B. After cancelling the terms, we get Ka square P divided by 1 plus Ka square P. As we know, P is equal to P is nothing but the average power of the message signal, which is AM square by 2. I'll just substitute it for P. As we know, here mu is modulation index of the amplitude modulated signal, which is nothing but KAM. I'll just substitute it instead of KAM in this equation. Then here the 2 will get cancelled, and we will get the final result equation of the figure of merit, which is nothing but mu square divided by 2 plus mu square. Thank you.